Okay, let's talk about density. And I think most people are familiar with density in terms of like a science, maybe Science 9, where you might talk about the pounds per cubic foot of something or the kilograms per cubic meter. You're typically talking about a three-dimensional density things, but I just remind you that we can talk about density in terms of all three dimensions. So we can look at linear. Right, we can look at a linear density, and that's typically the variable lambda. And we could do a variety of things, but let's say we're going to look at a linear density, and then we're going to look at the kilograms per meter of some board or something. We could also look at, I don't know, the cost per linear foot of rope, right? You go into Home Depot and you want to buy some chain or some rope. It's so much money per foot of rope or per foot of chain. Or floorboards, it's so many, it's a linear thing. Certainly we can characterize a board as so many kilograms per meter. Then we could look at an area density, which is typically sigma. That could be, lots of times that's people per square mile or something. You could be buying carpet, and that could be a cost per square yard or something, right? It's an area density. And then we can do volume, right? Three-dimensional density, which is typically rho, lambda, sigma, rho. And these variables are pretty consistent across math and science. And this is the volume density. So this could be pounds, which is a unit of weight, per cubic foot. This could be a massed three-dimensional density, so kilograms per cubic meter. Or we could even look at, let's say, the charge. So let's say we have some insulator and it's charged. It's so many coulombs per cubic meter or something. Right? We can talk about water. Water's density. You talk about water's density is one. And again, think about the units there. So 1 kilogram, 1 liter of water weighs 1 kilogram. So that would be water's density, 1 kilogram per liter. And a liter is a measure of volume, 1 kilogram. Well, a liter is 1,000 cubic centimeters. Well, then 1 kilogram is really 1,000 grams. So we have 1,000 grams are in 1,000 cubic centimeters, which is also to say that there's 1 gram of water per cubic centimeter of water. So we can all talk about that, and I'm sure that's come up before. Okay, so let's use this in terms of how this relates to calculus. Okay, let's do linear first, and so let's just take a board. Let's take some board, and let's make it easy at first where we don't need calculus. Okay, the non-calculus version says, okay, let's say that the linear mass density of this board is 5 kilograms per meter. Let's say the length of the board is 4 meters. So then what's the mass of the board? Well, if it's a uniform density thing and there's 5 kilograms per meter and there's 4 meters, of course then that as a board is 20 kilograms. That's too easy. Okay, so let's flip it and make it, why do we need calculus? Well, what if lambda wasn't a constant? What if lambda was equal to 6x? Lambda was some function of x. And so if you think about what's happening here, the density is growing, getting bigger as we move further and further along on the board. So we take this board and we divide it up into really small segments. And again, these are infinitely small segments, and we could talk about each segment. So if you talked about this amount here, right, that's kind of where x is 0. Well, that'd be kind of almost have no density, okay? And then if you looked way over here, when x is 4, at the very end of the board, the density would approach 24, right? 4 times 6. So at the beginning, you almost have no kilograms per meter, right? The density of that part. And at the end, you have something that's super dense, like 24 kilograms per meter. And so the question is, what's the mass of this board? Okay, well, the mass, using calculus, is really easy. It's just summing up all the individual masses. So we take this board and we break it up like we did into a bunch of really small pieces, where each little piece, right, each little piece has its own mass that we call dm. Okay, so how is dm related to lambda? Okay, and that's where the home run hits here. Okay, so what is dm? Well, each little mass is the density times the thickness. Think about that for a second. The mass of each piece is the density of each piece times the thickness of each piece. Kilograms equals kilograms per meter times meters. dx then represents the actual thickness of that piece that has a mass of dm. dm represents the little bitty mass, and dx represents the little bitty distance. But if you take the kilograms per meter times the number of meters, you get back the kilograms of each thing. And so if we need to sum up all these dm's, then we need to integrate from 0 to 4, where dm is lambda, which is 6x times dx. 6x gives you the density of each piece, dx gives you the thickness of each piece, 6x times dx gives you then the mass of each piece, and then we need to sum up all of those. And so we do that integral and get 3x squared, and evaluate it from 0 to 4, and then we get 16 times 3, and we get 48 kilograms. Okay, and again, this is a linear density thing. We're going to do the very same thing. Again, dm is lambda times dx. We'll do the same thing, except now we'll do an area thing. Okay, so let's do area, and for area, instead of mass, let's use population. Okay, so let's say we have this city, and the city is really close to being a circle. And let's say the population density is some function like 10 minus 2r. Okay, so what does this really say? Well, what's the density when r is 0? Right, you get a 10, and again, that'd be people per square mile. So when we're really close to the origin here, we have a very big density, 10 people per square mile. Well, it's not really a big density, but let's assume it is. And then sigma of 5, well, we get 0, which means once we get here, no one lives on the perimeter of the city. And you got to think about, well, the density then decays. So the city has a ton of people here, and then less people, and then less people, and then less people, and then almost no people. You can almost then assume that the radius of the city then is 5, considering the density goes to 0 when r is 5. So lots of times we use capital R to represent the radius of the city, where r represents kind of our function. Okay, so how do you find then the population? Well, the population, what would you do if the population was constant? Or excuse me, what would you do if the population density was constant? Well, you would take the density times the area. The people per square mile. If you told me the area of your city, then I could find the population of your city. But this won't work in this case because sigma is a function, right? It's not a constant over that area, so we can't just take sigma and then multiply by the area. We have to use calculus. And so the population really in this case is the integration. We're going to go from 0 to 5 of what? Well, how are we going to break this city up into pieces? Well, remember, for our board, we broke it up into little bitty segments. Here, we're going to break it up into rings. And why rings? Well, if you think about this, if our population density is some function of r, as we get further and further and further away, we're at some density. But if you look at an individual ring, everywhere on that ring is at the same distance away from the origin, that population density is the same. So we can take that area, so this is some dA, so instead of being dx, it's some dA. dA represents the area of that ring. So you come down here and you're like, okay, what's the area of the ring? Well, it turns out that if you take that ring and you make it into a rectangle, this length is just the circumference. And that is just the thickness, which is dr. dr is how much you're going, dr, dr, dr. And so then the area, of course, is 2 pi r dr, which is also just the differential of an area equation. Okay? And so what we need to do here is we need to take sigma times dA. Think about what we're doing here. We're summing up each individual area, dA, times its own individual sigma, which is a function of r. That gives you the population in that small segment dA, and then we sum up all the populations to get the total population. So we need to integrate from 0 to 5 of 10 minus 2r. That gives you the population of each individual thing times dA, which is 2 pi r dr. And then you just do that integral. Again, if you were doing this integral, you might want to distribute this first. So we get, what, 20 pi r minus 4 pi r squared dr from 0 to 5. Integrating this, power rules increase the power divided by the new top power, so we get 10 pi r squared minus, what, 4/3 pi r cubed, and then evaluate from 0 to 5. And you'd get some number. Again, it'd be some number. Again, we can type that out. So 10 times 5 squared minus 4/3 times 5 cubed. 5 cubed. Let's do that again. 10 times 5 squared minus 4/3 times 5 cubed. Whoa. Keep messing this up. That's terrible. And we get like 83 1/3, which is 250 pi. So let's round it to the nearest person. So that's 262 people. Again, the population is the number of people that would live in that little bitty village. It looks like this is a village more than it is a city. Okay? All right, so think about what we did here. Very similar. So in the linear case, we did lambda times dx. Well, here we're doing sigma times dA. dA is the area of each individual one of those rings, where dx was the width of each one of our segments. And then the next case is our three-dimensional case. Our three-dimensional case, well, now let's look at a 3D case. So let's look at some sphere. Okay, I'm not very good at drawing, but that's some sphere. And let's say we're charging it. It's some insulator. So we'll relate this back to physics. It's some insulator, and it has a charge density of 2 plus 3r. So at the very inside of this sphere, it's charged at like 2 coulombs per cubic meter. So this is coulombs, which is our unit of charge, per cubic meter. And then as we get further and further away from the origin, right, spherically outward, those are all spherical little shells here, then our charge density grows. Okay, so let's say that we have a radius of, let's say, 4 meters, and I want to find the total charge on that insulator, or enclosed in that insulator. Okay, so the total charge, well, what would you do in an easy case? In an easy case, if the charge density wasn't a constant, you would just take the density times the volume. But we can't do that in this case because the density isn't uniform throughout the entire volume. The density changes. So we use calculus. And the calculus says what we can accumulate the density times dV. dV being the individual volume of each individual shell. And here, dV is the volume of each volume of each shell. And if you think about the volume of each shell, right, make these shells. Okay, that's a terrible drawing, but you're going to have to bear with me on that. 4 pi r squared dr. The surface area of each shell, again these are spherical shells, is 4 pi r squared, and then dr then is the thickness of each one, and so then the volume of each one is 4 pi r squared, which also, if you just take the volume of a sphere and take dv, of course you get this same thing. So what we need to do, we're going to integrate from 0 to 4 of the density 2 plus 3r, the density times the volume of each individual shell. The volume of each shell times the density of each shell gives you the charge on each shell, and then sum up all of those individual charges to get the total charge. And then this integral is the same thing. We don't need to work it all out. I would suggest again multiplying this out and getting 8 pi r squared plus 12 pi r cubed, and then integrating, and then going from there. Again, the same thing. All of these things are very similar in terms of what we did. So in the linear case, we found that the total mass was the summation of all the dm's. Each dm, though, was its linear density times some thickness. Again, kilograms per meter times meters. In the area case, the total population was the accumulation of the sigma times dA. And then the charge case, the charge was the accumulation of the volume density times dV. They're all very similar. This is linear, this is area, and this is volume. But again, all of these are necessary when the charge density, the area density, or the linear density are functions. Functions of x, functions of r, functions of something. Because if they weren't, well then we could just go old school. The total charge is easy, it's just the density times the volume. The population is easy, it's just the density times the total area. But if the density is a function of the area or a function of r, then we have to use calculus. And that's the beauty of calculus, that it allows us to break things up into little bitty pieces. Here, again, we broke the board up into little bitty things that each have their own thickness dx. Here, we broke our city into rings. Each ring has an area of dA. And here, we broke our sphere into spherical shells. Each shell has a volume of dV. Okay, hopefully this helps you out with density. Again, this is going to be, you're going to use this in calculus, you're going to use this in physics, you're going to use this concept in engineering all the time.